if a moving charge can be pushed or pulled by a magnetic field, is it reasonable to expect that a moving charge could create a magnetic field? Well, if we believe Newton's third law, yeah. I mean, if I hit you with a normal force, you hit me with a normal force. If that moving charge can experience a magnetic force, it can exert a magnetic force. Now, this was discovered first by a scientist named Ørsted, Hans Christian Ørsted. He's got an itch there. I love this story because this is a case, maybe the only case, where a very important discovery was made during a lecture. I mean, usually nothing good happens during a lecture, but Ørsted was lecturing, as the story goes, and he had a voltaic cell that he was causing current to go through conductors with. And then he just happened to have a lodestone nearby. A lodestone is just an old school compass. It's just a rock that happened to be magnetized. If you hang it from a string, one end of the rock always points towards Hudson Bay. So what I've got here is a compass next to a wire. And let's move that. And right now there's no current in that wire. But if I close this switch, suddenly there's current and it creates a magnetic field. And that field goes a certain direction. The compass is underneath the wire. If I were to hold that compass above the wire and do it again, it goes the other way. Okay? Now you saw this when you were playing with the compass and the wire in tutorial this week. Now, if we were to make that wire go vertically and put a bunch of compasses around the wire, what we find is that the compass needles all line up in a circle, technically tangent to a circle. And so what we find is that the magnetic field lines, due to a long straight wire, are always circles that close on themselves, perfect circles. Now, I can never remember which way they go, clockwise or counterclockwise, and so I have developed a memory device. Actually, it was thought up long before I was born. But this memory device uses, again, the right hand. And the right hand has a straight part and a curved part. If the current is traveling in a straight wire, use the straight part of your right hand to represent the current. The curved part of your right hand will remind you which way the field lines wrap around that wire. So here I'm using right hand rule number 2. Right hand rule number 1 gives me the direction of the magnetic force. That's the reach, turn, wave. Right hand rule number 2 is just a memory device, like tying a string to your finger to remind you to bring a loaf of bread home from the store. Okay? Now, let's look at the magnetic field due to a wire carrying current. If I look right here, that field, by this right-hand rule number 2, is going to be out of the page. If the field lines wrap around the wire, they would go into the board down here and out of the board up there. So that would be out of the board. Up here it would also be out of the board. Down here it would be into the board. And there it would be into the board. Now this representation, this side view, doesn't tell me anything about the magnitude of these fields. And so it's going to be better to draw this on an end view where the current is coming towards you. In that case, the magnetic field there, by right-hand rule number 2, would be to your left. Right there, it would also be to your left, but it would be weaker. Down here, it would be to your right, and here it would be to the right, but weaker. Now, we're not going to go through the derivation. It involves some messy mathematics, But what we find is that twice as far away from a wire, the field is half as strong. So it falls off linearly with distance away from the wire. Now, let me just remind you the difference between the magnetic field lines and the magnetic field vectors. The vectors give you the magnitude and direction of the magnetic field at one location, at the tail of the vector. The field lines represent the magnetic field all throughout the room. And so, if I wanted the magnetic field right here, it would be a vector that was tangent to that circle. So it would be going that direction. If I wanted the magnetic field here, it would be tangent, it would be going that direction. If I wanted it here, it would be tangent, going that direction. Okay?